I'm just ready to start here.
Okay.
Good morning, everyone. Welcome to the 40th Soar workshop. And we're going to start off this morning with an introduction to Soar from Professor John Laird of Michigan. John?
Thanks, Peter. This is going to be the shortest SOAR workshop and also the one with the most attendees. So it's a real interesting time for us. So if you're interested in SOAR, and hopefully you are because you're attending this, the best source of information is the website at the bottom that contains all our software and also pointers to a lot of our publications over the years. Also, it provides access to the community at large. So highly recommend that you look at that. So let's get started. So SOAR started out as my PhD thesis when I was a graduate student at Carnegie Mellon University working with Alan Newell. Here's me in younger days. That's me on the left, Paul Rosenblum and Alan Newell. Paul was my partner in crime at the time. He worked on aspects of chunking and also an architecture called ZAPS that was the basis of the first version of SOAR. A few years ago, in 2012, published a book on the SOAR cognitive architecture, and I would say that's still the definitive overall publication on SOAR. So if you want to learn more about SOAR, I highly recommend that. So what is the goal of SOAR? So the idea originally was to support the development of multi-method, multitask, knowledge-lean to knowledge-rich agents that interact with the world in real time. So let's unpack that a little bit. Most AI systems at the time only worked on a single problem and used a single method. And with SOAR, we were trying to develop a system that could work on many different tasks, could use many different methods, and was able to have both knowledge-lean performance, which would lead to search, but also knowledge-rich performance, similar to expert systems, so that it didn't have to do search, and that we supported interaction with the world in real time. Our work was inspired a lot by cognitive psychology, but also computer science. We looked to psychology for useful cognitive mechanisms and capabilities, and computer science and AI for efficient and robust implementation. And both of these have been combined together in SOAR throughout the years. One of the key aspects of SOAR is we've been focusing on complex behavior and tasks, sort of longer time scales instead of just 1 to 2 seconds. And that includes both low and high level cognitive capabilities, those that Kahneman talks about as system 1 and system 2, but also beyond system 2, which normally is just sort of deliberate minute to minute reasoning. We also want to have agents that can do long-term tasks. Learning has always been an important part of SOAR, and our emphasis over the years has been to expand that to many different sources of knowledge, just not one source, and many different types of knowledge. And also a really important part is always emphasizing efficient real-time execution, even when the system scales up to large amounts of knowledge. When we're modeling human behavior, the execution time needs to match about 50 milliseconds for this basic cycle time of SOAR. But SOAR on a laptop, I have an old Microsoft Surface Book. It runs close to 100 times faster than real time. So let's do a little bit of history of SOAR. SOAR started, as I said, working on multiple tasks and multiple methods. Here are some of the capabilities we've tried to incorporate into SOAR throughout the years. As we go through the workshop, we'll hear more and more about task learning, and that's been a very big emphasis on the work at Michigan over the last 5 or 6 years. Along the way, we've been developing architectural mechanisms to support those capabilities. We started with symbol systems, problem spaces, chunking a learning mechanism, and so on. We had a burst of activity around 2005 where we added a lot of new mechanisms, including reinforcement learning, episodic memory, semantic memory, and mental imagery. And recently, we've had a new version of chunking developed by Mazen Asani. So that we continue to work on both of those, and we've had many applications, initially toy problems, but then an expert system. We've done robotics, We've done a lot of synthetic entities within simulations, computer games, and even autonomous vehicles, and natural language. So we've been doing a lot of different tasks over the years. So our research methodology, if you look at the kinds of research we do, you can sort of break it into two parts plus one. One of them is on architectural mechanisms, as I talked about earlier, exploring new architectural mechanisms and major extensions to existing ones, where an emphasis has always been on developing implementations that scale to large knowledge bases. We've also been looking at these cognitive capabilities that are on top of the architectural mechanisms, with a lot of learning being important, and then tasks. Tasks that really require the integration of many of these architectural and cognitive capabilities. Interactive task learning has become a primary application for us at Michigan because it does require the use of all these different architectural mechanisms and a lot of different cognitive capabilities. So over the years, we've had an ongoing originally Soar was implemented in Lisp, but for the last many years, over 20 years, Soar has been implemented in C. We're currently up to version 9.6. That's implemented in C++ and is available on Windows, Linux, and Mac OS. This is the cutting edge version of Soar. So this incorporates all the most recent advances in Soar implementation, and is very efficient in terms of memory and execution speed, and it's maintained and released through the University of Michigan. There's also a Java-based version of Soar. The fact that it's 9.0.4.0.2 does not mean that it's 5 versions behind CSOAR. This is that version of JSOAR. It's implemented in Java and is available on Windows, Linux, Mac OS, and Android. It does trail the CSOAR implementation. It's around 9.3. There are some aspects of episodic memory, semantic memory, and chunking that are a little bit behind, but it tries to be an extremely faithful dual of the CSOAR implementation. Its advantages are it has better support for using many different languages for multi-threading, and it has a cleaner integration with enterprise systems. So this is maintained by Soar Technology. Overall, there's hundreds of tasks implemented in Soar. Just to give you an idea, these are just ones that I have pictures of. There's many implementations of Soar in different virtual environments. So computer games, we have a system that plays liar's dice on an iPhone. We've done video games and other types of applications. We've also done lots of work at Soar Tech, where this is also done in a lot of virtual but also robotic environments. Here are some of the robots that have been developed over the years using Soar, many of them at Michigan, but also some at Penn State, and also at Soar Technology, and also other places around the world we didn't even know about until we got videos from them showing that they've been using them. So a lot of work in robotics and Soar. Some of the recent embodiments of Soar at Michigan, just to show that we keep going into new areas, we have been hooked up to a bunch of different simulators. April is a group that is led by Edwin Olson at Michigan, and we've taken advantage of both simulators and real robots he's created over the years, so give him a shout out for us being able to, for the support he's given on us in terms of integrating with that. We also recently integrated with AI2 Thor, a simulator available from the Allen Institute of Artificial Intelligence. And also here are some example robots, the Fetch being a commercial one. This is the Magic Bot developed by Ed Olson's lab, and this is a specialized robot arm also developed by Edwin's group that uses the Kinect vision sensor. So let's dive into Soar, the structure of Soar. The early version of Soar had a symbolic working memory as where it represented its current situation. It then also would be able to take in perception from the outside world and do action. But its one long-term memory was its procedural memory, where knowledge was represented as rules. In contrast to rule-based systems at the time, Soar did not try to pick the best rule to fire at one time, called conflict resolution. Instead, it picked what we call an operator using a decision procedure based on parallel rule firing. And so we're going to dive into this as we go forward and explain how Soar uses rules in order to make decisions. But we'll later on expand the other aspects of Soar, including semantic memory and episodic memory. So what is the basic idea behind how SOAR does reasoning? This is derived from the problem space hypothesis from Alan Newell, which says that problem spaces are the basis for all goal-based reasoning. And so let's just sort of go through that at an abstract level. So at any one time, the system is in a state. This is the situation it's in the world. That can be derived from its sensing, but also from things it recalls from memory. And in our case, this is what's represented in working memory. It's going to use knowledge, and initially that in SOAR meant rules in order to understand what are the possible actions it can perform at this time. And those are called operators. So it would propose, so SOAR proposes different operators and says, here are the different things I can do. And we'll go through a specific example with blocks world in a minute. We also then are using knowledge in order to decide which of these operators should be selected. And those is also encoded as rules. And then one operator will be selected. Once that operator is selected, once again, the system will use knowledge encoded as rules in order to apply that operator in order to actually change the current state. Now this sort of shows that we're generating a new result, but it's actually modifying that existing state. And this, not sort of coincidentally, is where we get the name for SOAR. State, operators, and result is the basis for the name of SOAR. We don't advertise that a lot, but that is where SOAR comes from. Once we've got a new result, this whole process continues where knowledge comes into play in order to generate operators and so on. So let's look at that just a different way. So here is the basic processing cycle laid out as a flow chart or data flow. So we have input coming in from the system. We have rules firing parallel to elaborate that situation, to notice features that are important. We then have operators that are proposed by rule firings. Operators are evaluated. These create what are called preferences that are used to rate how good the operators are and compare them to one another. There is then a single operator selected, and then rules fired to apply that operator. That operator change might occur internal to SOAR, or it might lead to output, which then goes back and we then go through input. So we go through this cycle. And this is the basic cycle in SOAR. And the idea is that that occurs for modeling human behavior at about 50 milliseconds. But when we're running on today's computer, it runs, say, 100 times faster than that. So there is no additional mechanisms that could come into play here, like a planner or something else, although you could, through output, call a planner, get input as a plan or whatever. But the basic SOAR operation is like this. So complex behavior arises through going through this multiple cycles. And then the processing in each cycle is bounded to maintain reactivity. We found in robotic applications that has to be about 100 milliseconds, which of course is much, much slower than SOAR runs, but that is what we found, that for robotic applications between 50 and 100 milliseconds is a good bound. So let's jump in and look at a specific example. So here is about the simplest example I could think of, which is the blocks world. So in working memory, we're going to represent what our current situation is. Here we have 3 blocks total. We have C on the table, A on the table, and B onto C. So this is maybe the logical representation that's going to be in working memory. We also have a goal we're trying to achieve, which is A on B, B on C, and C on the table. So remember the basic reasoning cycle that SOAR has. The first thing that's going to happen is we're going to find rules that match the situation and do elaborations. And so the first rule is if a block does not have a block on it, then it is clear. That will elaborate the situation, adding more structures to working memory, that B is clear and C is clear. Then we will go into the operator proposal phase, where we have these proposal rules. If a block is clear and a second block is clear, then propose moving the first block onto the second block. So this would propose moving B onto C and C onto B. We'd also have, as a block is clear, then propose moving that block to the table, moving B onto the table. It should have also had the condition that the block is not already on the table, so that we don't propose moving C onto the table. When these rules fire, they create in working memory proposals for these 3 operators: moving B onto C, moving B onto the table, and moving C onto B. From there, we have a selection rule that says if an operator is proposed to move a block onto its goal location, then it is best. And that creates a preference that C onto B is best. If an operator is proposed that does not move a block onto its location, then it is indifferent. And we have these ones. We then go into operator selection, where the system evaluates these preferences and determines that it should select move B onto C. From there, we're going to have application, where a rule will match and change aspects of the state. We'll remove that B is on A and add B is on C. So that happens, and we change the state there. We then continue on this cycle with elaborations, proposing additional operators, and so on. So that is the basic cycle, and it would continue on, say, moving A onto B, and we would finally achieve the goal. So this also could happen through an external operator application. So say we move B onto C, but we don't have rules to do that. Instead, what happens is that we have a rule that sends a motor command to move B onto C, say for a robot arm. That would go to the action system. That would then change the world by actually doing the movement. And by perception, we would then perceive the change and end up with this new situation. And so now you can see that B is onto C, and we continue on as we did before, but instead of doing this internal, we'd actually do it in the external world. All right, so we assume now that the system has all the rules it needs to do that basic cycle. But in many cases, some of that knowledge might be missing. So if that knowledge is missing or in conflict, what happens in Soar is what we call an impasse. And when Soar encounters an impasse, it automatically creates a substate and then recursively applies the problem's reasoning in that substate, meaning we're going to do operator proposal, selection, and application. So let's look at some examples of that. So here we have the simple blocks world, but in this case, we're going to assume that move B onto C is not a primitive action that the system can perform, and instead it must decompose that into moving a gripper around. So once we select move B onto C, there's actually no rules that know how to do anything with that. In that case, we're going to expand working memory because we need more size for this. And then we don't know how to generate the state. So that's going to get an operator no change impasse. We're going to then go into a substate. In this case, the state we have, we're going to reuse the state we have right here. We're going to have a new goal, which is to apply this operator, which is to achieve B onto C. And then we're going to select an operator. I'm not going to show the rules to do that, but there would be rules to do that. It says if we're trying to achieve B onto C, then we should pick up B. That then maybe we can't do that even. And so we're going to into subburst state, where then we actually have a gripper that is holding, that we're going to try to move. We're trying to actually get the gripper to hold B. And so we have to select an operator that moves B, move the gripper above B. And so you can see we're going to decompose this. So if we look at this more abstractly, there's the move operator. That can be decomposed into sub-operators of pick up and put down. And those can then be decomposed into even more primitive operators that have to do with moving a gripper around and opening and closing a gripper. We can also think about how move can be part of a more abstract operator or more complex operator than that, such as building a tower, where we initially select build tower, and we then move blocks in order to build a tower. So we can have that kind of hierarchy. Here's another hierarchy, which is for a room cleaning mobile robot. And just to show that this kind of hierarchy of operator no changes and decomposing into more simple operators. This is appropriate for actions that are going to take place, pretty quickly. If you're going to think about achieving goals like going to graduate school or getting a new job, those are probably not best handled in this kind of approach of selecting an operator that's going to need to persist in working memory for a long time. So that is sort of more a task-oriented selection and changing of tasks more deliberately. So let's go and look at another aspects of doing abstract operators. Say we want to move B onto C, but we don't want to do it ourselves. In the subspace, we might actually issue a command and ask a human, please move B onto C. Or we might actually say, well, I seem to remember once before I did move B onto C. I can't remember how I did in the past. So we might go and access episodic memory. Just to show that in these substates, we can use lots of different methods in order to solve those impasses. All right, now let's look at the situation where the rules are missing for picking between operators. So what happens if the selection rules are missing? This gets a little complicated, and I'm unfortunately going to have to go through it a little quickly, but here we go. So if we have something called a tie impasse. In a tie impasse, once again, we're going to go into a substate. In this case, we're going to have use knowledge encoded as rules for what we call the selection space. In the selection space, we're going to explicitly evaluate each of these operators in order to determine whether it helps us achieve this goal. We start by selecting evaluate operator and move beyond a C. And that we can't do immediately, so we go into a substate, and then we make a copy, not using the same state, but using a copy of that state. And then in the substate, we actually try out moving beyond a C and see what happens. So we're not actually changing the world up here. We're actually doing a look-ahead search. We find that moving beyond a C does get B into the situation that we want to here. We then give that an evaluation of 1 because we've achieved part of the goal. That gives us an evaluation for this operator of 1. We go and evaluate the other alternatives. They don't really do anything in helping to achieve our goal, so they give us evaluation 0. We have other rules that I'm not showing that then compare these evaluations to create preferences. In this case, we create better than preferences or indifferent preferences between things with equal values. And this then leads us to being able to make a selection. And so one of the interesting things that happens in Soar is when you do create results from substates, Soar does an analysis of what was involved in that processing and builds a rule to summarize that processing. So after we do this once, we actually learn a rule that will create this preference in the future when we get to a similar situation. And so after all this, we will select B, C just as before, but we did all the substate processing in order to do it. So as you see in Soar, we have 3 levels of processing. We have system 0, which retrieves relevant information from memory. It matches the rules to the current situation. We have reactive decision making, which is proposing and applying operators. And then we have sub-goal processing, where we're doing more deliberate processing using a lot of different methods. And chunking in the background is converting system 2 into system 1. Let's look at what Soar does like right now. Here we have not only procedural knowledge, we have semantic long-term memory and episodic long-term memory. We also have the spatial visual system. To just give you an idea about this, we're going to go through a quick, simple example. So let's go to a situation where you are supposed to imagine the word wow. Now I want you to rotate that, and then I want you to take that, what you get the result, and think of the last time you saw the spouse of that person. And very quickly, this is what we imagine is going on in Soar when you're doing that. You imagine the word wow, this comes into working memory. You then look it up in semantic memory and get the symbol imagine wow. That then goes to find a skill for imagining things in procedural memory. That then imagines the word wow in spatial memory. We then get the rotate, go through that same sort of procedure, get a skill for rotate. Hopefully you have that, and you were able to do that. And then from that, you're able to extract out this new idea of symbol of mom, go access that in semantic memory, find the spouse, which is dad, go and look up episodic memory for dad, find that that was last Sunday or whenever. So that's supposed to give you a very quick idea of how all the different parts of Soar sort of work together. All right, so where are the neurons? Some people are asking where are the neurons in all of Soar? Well, there's not neurons today, but one can imagine there are places where we could add neural networks as that technology evolves and as we find ways of integrating with Soar. For example, in visual perception, we could use neural nets in order to do the perceptual processing and to create our representation of the world. We could imagine using neural nets such as transformers in semantic memory or in episodic memory, and even in procedural memory. The key issue is how do they get training and how do they get integrated with the symbolic working memory? So those are all possibilities for future research. Just wanted to give that an idea for you. All right, so here's a preview of the workshop. There's going to be 3 sessions today between 95 and 110 minutes. There's going to be individual talks between 10 and 30 minutes, hopefully with 3 to 5 minutes of questions. We're going to use the chat window to post questions, and sessions chair will then relay them to speakers. There'll be a discussion section at 4:15, where we open it up to ask questions from the broader audience. And after the workshop, we will post the videos and slides of all the talks and the list of attendees. And I want to remind you that VISCA 2020 is going to happen tomorrow and Friday, and you can go to this website in order to get more information. And let me stop and leave up the, here is just the schedule for the rest of today.